Okay, so picking back up where we left off. So we're taking a look at this problem. Okay, so they're asking us to determine number of protons, electrons, and neutrons just based on the chemical symbol for the isotope, or the isotopic symbol. Okay, so this first one, we have S. S is for sulfur, of course. So they're not asking necessarily to identify it, but it's good to go ahead and get familiar with those symbols if you're not. Okay, so they want us to determine the number of protons, electrons, and neutrons. Okay, so first of all, we need to know what do these two numbers tell us. So remember, the bottom number tells you the atomic number, which tells you the number of protons. Okay, so in the first one, we see the bottom number is 16. Okay, so that tells us our atomic number is 16, which tells us that we have 16 protons. Okay, and we don't have any charge, so if we did have a charge, we would see something right here. Okay, so there's no charge, so that means we also must have 16 electrons. Okay, they give us a mass number of 32, so all we have to do here is say 32 minus 16, and that's going to be the number of neutrons. Okay, so that's of course 16 as well. Okay, the next one we have copper, and we have 29, and we have 65. Okay, so first one, this will be our atomic number, which also tells us our number of protons, so all you have to do is just copy that number over. Also tells us our number of electrons, so also 29. And now again, we need to do 65 minus 29 will tell us number of neutrons. Okay, so if we do that math real quick, we're going to end up with 36. Okay, so no big deal. So as long as you understand what those two numbers are telling you, it should be fine. Okay, so next one, U240. Okay, so when we do symbols like this, they're expecting us to know a little bit more information. Okay, so this number is going to be the mass number. Okay, so remember that's the number of protons plus the number of our neutrons. Okay, so how do you determine the protons and the electrons? Well, for this, unless you just happen to know how much uranium has, you have to use a periodic table. So find on the periodic table, the atomic number will tell you number of protons, 92. And then you know that it's neutral, so it's going to have the same number of electrons, so also 92. Okay, and then if you just do the math, so 240 minus 92, that will give you number of neutrons, which is 148. Okay, so just from this symbol, you get all the, well, these at the top give you a little more information, but you can still determine all the same things from the symbol at the bottom. Sometimes you'll see it written that way, sometimes you'll see it written the way at the top. Okay, so let's move on. Okay, so here's another problem for you to try. So this is just a chart, and what I want you to do is I want you to go into this chart and try to fill it out. Okay, so for instance here, I have 6 protons. I'm assuming everything's neutral. How many electrons do I have? Well, I also have 6. Okay, and what's the atomic number? Well, I know that's equal to the number of protons, so that would also be 6. So what's my mass number? Well, that would be 6 plus 7. Okay, so 13. And what's my atomic symbol? That would be this. 6, not 12. Okay, so give this a pause and try to fill the rest of this table in, and then we'll continue. Okay, so hopefully you're able to fill out this chart. Let's take a look at it. Okay, so the next one, they tell us it has 42 electrons. So that means I have to also have, what? 42 protons. My atomic number is 42. Okay, so that lines up with my protons as well. So since I have a neutral compound, so I could have looked at the atomic number, or I could have looked at the number of electrons. So this should be the same. Okay, so they don't tell us how many neutrons we have. Okay, so if I don't know how many I have, then I have to assume that I have the same number of neutrons as protons. I'll also say 42 here. This tells us the electrons. Okay, so then I have my chemical symbol. So this part you would need a periodic table. Okay, so this would be MO. Okay, so mass number, or the atomic number, will still be 42. Now my atomic mass, my mass number, okay, so it's just going to be 42 plus 42, so 84. Okay, so that would complete that line. Okay, the next one, they give us the chemical symbol or the atomic symbol for the isotope, and they want us to fill everything else out. Okay, so let's start with the atomic number. So atomic number 13. So that tells me number of protons. That also tells me the number of electrons. Okay, now the mass number, 27. Just copy that straight over. Okay, so from there, if I want to find the number of neutrons, I subtract 13 from 27. Which will give me 14. Okay, so that's everything for that line. Okay, now this bottom one. Okay, so we have atomic number 55, and we have a mass number 133. Okay, so what are we going to do here? First thing we need to do is look at our periodic table and find element 55. Okay, so I'm looking at a periodic table, and I see that element 55, CS, cesium. Okay, now I want to fill in what I know. So I know that my atomic number 55 and my mass number is 133. So that finishes off the atomic symbol. So if I know my atomic number, I also know my number of protons and my number of electrons since we're neutral. Now all I have to do here is 133 minus 55. Okay, so that gives me 78. Okay, so that fills in the table. Okay, so hopefully you were able to get all of those numbers correct. Make sure you practice these. Really, just knowing what these two numbers tell you is really all you need to know. Okay, if you know that, then you can fill in a table like this. So make sure you can do this. And if I advance the slide a little bit, you can see if we were right. Okay, so did I make any mistakes? Let's go back. So I think I made a mistake in this one. Okay, so these two numbers were wrong the way I did it because I had this number hidden. Okay, so I don't know that without one of these numbers if you could have determined this. Okay, so if we go back to what I put, okay, so you see here I put 42 because we didn't know whether it was an isotope or not. Okay, so if I didn't have one of these two numbers, there's no way for me to know. Okay, so that if I didn't give you a mass number or a neutron number, then this would be correct. But if you had one piece of that information, then you could determine the other. Okay, but based on that, our answer was correct, but this is what they actually wanted. That's okay though. As long as you understand the process, that's what's really important. Okay, so now that we know how to interpret isotopic symbols, what's the connection between an isotope and atomic mass? Okay, so the observed mass of an element is a weighted average of the weights of all the naturally occurring atoms. Okay, so if you're looking at a periodic table, you may notice that most of those numbers are not really very even numbers. Okay, so in other words, something like carbon doesn't have a mass of exactly 12. It's very close, but it doesn't actually have a mass of 12. And you may be wondering, why is that? Okay, so the reason is that there's more than one naturally occurring isotope. Okay, so what we do is we take an average mass of all the isotopes, and that becomes its atomic weight. Okay, so the observed mass of an element is a weighted average of the weights of all the naturally occurring atoms. So the average mass is what becomes the atomic weight. And it asks us what information is needed to determine the atomic mass of an element. Well, what we need to know is the natural abundance of each of the element's isotopes. That is to say, the percentage of an element that is one isotope. It's called the isotope's natural abundance. Okay, so the natural abundance, okay, is just the percentage of an element that is one isotope. So in other words, if I have, one, so if I have just as many carbon 13s as I do carbon 12, that would be like a 50-50 or 50% natural abundance. Okay, that's not correct. I'm just using that as an example. Okay, but if we move on, so this is how we actually find it. Okay, so we say boron has two isotopes. So boron is 19.9% boron 10 and 80.1 boron 11. So if we take a look at our periodic table and we find boron, we see it has a mass relatively close to 10. Okay, but not exactly 10. Why is that? Okay. So boron atomic weight, well, closer to 11, I should say. Okay, so the atomic weight of boron is found like this. So what we do is we take a weighted percentage or a weighted average of all of the naturally occurring isotopes. So we just take our percentage, go 1, 2, turn it back into a decimal, and we multiply that by the atomic mass units, the AMU. So AMU is the atomic mass unit. In other words, the atomic weight of that particular isotope, okay, which again is just our protons plus our neutrons. Okay, but it's only 19 or almost 20% that, we'll say 19.9%. Okay, so multiply that times the 10 AMU plus, so we're adding all these together, so it's like a weighted total, you could say. Okay, plus 0.801 times 11 to give us 10.8 AMU. Okay, so that's the average mass. In other words, that's the mass we report based on the fact that we know it exists. 19.9% is boron 10, 11 or 80.1% is boron 11. Okay, so it's just a weighted total or a weighted average. You could, either way you want to look at that. Probably weighted total is the better way to say it. Okay, so just take the fact that we know it's almost 20% boron 10, almost 80% boron 11. Convert those to decimals and multiply by the AMU. Okay, so here we have a problem. So it says the element silver has an atomic mass of 107.868 AMU. It has two isotopes, silver 109, and they give us the weight of that, and the abundance, and silver 107. And they want us to determine the weight of silver 107. Okay, give this one a try, and I'll go over it with you, see what you come up with. Okay, so let's take a look at this one. How will we go about solving this? So the first thing I'm going to do is I just want to write down the information that they gave me. Okay, so the first thing they told me is that I have silver, okay, so I said silver has an atomic mass of 107.868 AMU. Okay, so that's what everything has to add up to. And it tells me it has two isotopes that we're looking at. So silver, and this is going to be 109, and silver 107. Okay, and they give me the atomic mass for this one, 108.905 AMU. And this one I don't know, so I'm just going to put X. Okay, they tell me that silver 109 is 48.16% abundance. And the other one so they don't give us the percentage for the other one, but essentially I can say 100% minus 48.16, and that's going to give us an abundance of, let me see here, so 51.84%. Okay, so now what can I do? So now I can set up an equation. So they're asking me what's the mass of silver 107. So what are they really asking me? They're basically asking me to solve for x. Okay, so I can set up an equation. And the equation I'm going to set up looks something like this. Okay, so I'm going to say that I have 0.48, and then just keep going as far as I can, 16 times 108.905 AMU. So that's this information for silver 109. Okay, and then plus I have 0.5184 times x. And this is all going to be equal to I'll be equal to 107.868 AMU. Okay, so what we need to do now is solve for x. Okay, so if you go through and you do some simple calculus here, what you'll end up with is 0.5184. Work with me. 4 times x is equal to 55. Tablet is not doing what I want it to do right now. Come on now. There we go. $55.4180. And if you solve for x, okay, I end up with 106.905 AMU. Okay, and that would be my final answer here. So that's what we were asking for. So we just want to determine the mass of silver 107. So as long as we understand how atomic mass is calculated, we can set up something like this. And if we had 10 isotopes, we could set up the same thing, okay, if we were just missing one. But the calculation is the same, whether I have 2 isotopes, 10 isotopes, 100 isotopes, it doesn't matter. Okay, they're just weighted totals. Okay, so that's all on isotopes for right now. Let's move on, and we're going to talk about ions. Okay, so what is an ion? Ions are atoms or groups of atoms with a positive or a negative charge. Okay, so it's essentially a charged atom or a charged molecule. Okay, and they come in sort of 2 flavors here. So if we take away an electron, we're going to get a cation. In other words, we're going to get an ion with a positive charge. Okay, so in this case, we have more protons in the nucleus versus the electrons that are surrounding it, giving us overall a positive charge. So metals are going to tend to do this. Okay, so your metal atoms, and we'll talk about sort of at the end of this chapter, what are metals, what are nonmetals. Okay, they're generally going to form cations. Now if we add an electron, so if we add an electron before we took away electrons, we're going to form an anion. Okay, so if we take away an electron, we form a positive charge, cation. If we add electrons, we form a negatively charged anion. Okay, so anion is a negatively charged ion. Cation is a positively charged ion. Okay, so we end up with fewer protons in the nucleus versus the electrons surrounding the nucleus, so we end up with a negative charge. Notice in all of these statements I said electrons. Okay, so adding electrons or removing electrons. We never add or remove protons. We're only going to talk about adding and removing electrons. Okay, this is typically going to be your nonmetals. Okay, so your nonmetals will typically form your negatively charged particles, or negatively charged atoms. Okay, so let's break this down a little bit. So first of all, cations. So cation forms when an atom loses one or more electrons in its outer valence shell of electrons. So the outer electrons, in other words, the one on the outermost of the atom, referred to as the valence electrons. And this is where all of the sort of story happens. This is where You're going to have reactions taking place. This is where you're going to be adding and removing electrons. So this is where everything happens. Okay, so it's out in the valence. Okay, so here we have the example of sodium becoming sodium 1+. Okay, so remember that cations are positively charged because the atom has one more proton, or one or more proton, compared to the electrons. Okay, so here we have an example of magnesium. So it normally has 12 protons and 12 electrons, but if we have Mg2+, magnesium 2+, it still has 12 protons, but now it only has 10 electrons, giving it an overall +2. Okay, and this is typical with metal elements. So magnesium is a metal element. Okay, so the example again, so neutral magnesium, notice that nothing's written here. That means it's neutral. Okay, so it's losing 2 electrons to become doubly positive, so 2+, and notice that it's giving off 2 electrons. So if you remember, go all the way back to not creating or destroying matter. So when you're forming ions, you're equally not creating or destroying matter. So if we take a look at sodium here, so if you were to count 2, 4, 6, 8, 10, 11, that 11th electron is its valence. Okay, so it has 11 protons, 11 electrons. Okay, and what we're going to do is we're going to form sodium +1. Okay, so we're going to lose 1 electron. So notice now in this outer ring where that electron was, there's nothing. Okay, so we've lost our outermost valence electron. Now we still have 11 protons in the nucleus, but now we only have 10 electrons. So if you do that math real quick, you ended up with a +1. Okay, so we have one more proton than we do electron, so we have a +1 cation. Now with anions, we have a similar situation, but in the reverse. Okay, so an anion forms when an atom gains one or more electron into its outer valence shell. Okay, so anions are negatively charged because the atom has one less proton compared to its electrons. So for instance, fluorine atom has 9 protons, 9 electrons, but F-1 has 9 protons and 10 electrons. Okay, so it just has one more electron than it does a proton. Okay, this is typical of nonmetals. Example again, fluorine gaining an electron to become fluoride. Okay, if we look at our sodium and chlorine example again, okay, so what are we doing when we're reacting sodium with chlorine? Okay, so we know this is this is a salt, so it's an ionic compound. Okay, so we're adding sodium and chlorine together, and we're letting them react. So what's happening? So our metal, so sodium is our metal. So sodium is going to give up an electron to our non-metal, chlorine, to become chloride. And we end up with Na+ and Cl-. So that's just an example of how you might form an anion. Okay, but just understand cations form ionic compound, I should say. So just remember, cations give up electrons, or they have given up an electron. Anions gain electrons, or have gained an electron is a better way of saying it. Okay, so this is the same information, but just side by side, so you can compare it if you would like. Okay, so that's just the basics of anions and cations. We'll get deeper into that as we go on. But now we're going to move into the periodic table. Okay, so a historic perspective. Okay, so the original periodic table was developed by Dmitry Mendeleev. So he developed the modern periodic table. I shouldn't say the original, but the modern periodic table. Okay, and he argued that the element properties are periodic functions of their atomic weights. Okay, so he came up with what we call periodic law. Okay, so when the elements are arranged in order of increasing atomic mass, certain sets of properties reoccur periodically. So that is that word periodically, giving us periodic table. Okay, so elements having similar physical and chemical properties fall within a column. Okay, so what he's saying is that if we arrange the elements in increasing atomic mass, you're going to notice that some properties start to repeat themselves. And if you arrange those into columns, you're going to end up with columns of elements that have similar properties. Okay, so we now know that the element properties are periodic functions of their atomic numbers. So he said atomic mass. We now know it's their atomic number, meaning the number of protons. Okay, so it's an important distinction there. So one based on, remember, protons and neutrons, one based on strictly on protons. So now modernly, we arrange this by atomic number. So in other words, the number of protons. So this was sort of his original idea here. So if we look here, we have lithium, sodium, potassium. So that's our group 1 or column 1. Okay, and what we know is that these all have very similar properties. And we'll take a look at that in just a moment. But just keep in mind, so things like fluorine and chlorine or halogens, those have similar properties than our noble gases, helium, neon, argon. These all have similar properties. So just arranging them by their atomic number, or as he did by their atomic mass, starts to give you these columns that start to have similar properties. Okay, so this is a more modern looking periodic table. Okay, so the elements are arranged from left to right in increasing atomic number. Okay, rows in the periodic table are referred to as periods. So rows, in other words, going left to right, are periods. Okay, and then the columns with the periodic table are sometimes referred to as families. Okay, so up and down, these are going to be your columns, also called your families. Also called groups. And these are going to be your rows or your periods. Okay? So just depending on who you're talking to, they may call them one of those. Okay, so because the elements within a column have similar physical and chemical properties, they're referred to as families. Okay, sometimes also groups. The elements, their names, and the symbols are given on the periodic table. Well, of course, we know that already. Okay, so let's look at the major areas. So the first one is the metals. Okay, so we have the main group metals, and we also have the transition metals, and then we have the inner transition metals, which are the lanthanides and the actinides. Okay, we also have metalloids, and we have the nonmetals. Okay, so these are three major areas. Okay, so let's take a look at this. Okay, so we have our metals labeled in this sort of tan yellow color, our metalloids in this sort of lavender purple color, and our nonmetals in the greenish blue. Okay, so everything you see in this sort of khaki color or tan color, so these are all going to be metals. And you notice there's sort of a zigzag there. Oh, I kind of missed it, didn't I? Let me try that again. Okay, and that includes down here your inner transition metals. Okay, so those are all going to be your metals. Okay, so we'll break that down further in just a moment because we have main group metals, we have transition metals, and we have inner transition metals. But those are all metals. So these are things like that you're familiar with: gold, copper, lead, strontium, sodium, potassium. These are all metals. Okay. And then we have in the purple color, we have the metalloids. So you notice this stair step down the periodic table. Okay, that's where our metalloids live. So they're kind of in between our metals and nonmetals. Okay, so depending on which periodic table, sometimes they draw this line a little bit different. But basically everything along the dotted line, those are going to be your metalloids. Okay, and then lastly we have our nonmetals. So everything in the green color. Okay, so those are going to be all your metals. Or your nonmetals, excuse me. Okay, so these are like sulfur, carbon, iodine, bromine, your halogens. Okay, whereas your metalloids will be things like silicon. That's one of the reasons why we use it for things like computer chips and all this. A lot of these metalloids are useful in areas like that. Okay, so those are your three basic groups. Let's break them down a little bit further. So metals. Okay, so I have some nice bars here of our Olympic metals, so copper, silver, and gold. Okay, so characteristics. So they're going to be solid at room temperature, aside from mercury, of course. They generally have a reflective surface. They're shiny, in other words. We know that they conduct heat and electrical current very well. Okay, and they're malleable, meaning we can shape them into things like rings or coins. They're ductile, which means we can stretch them into wires. Okay, and we know they lose electrons to form cations. Okay, so about 75% of the elements on the periodic table are our metals. Okay, so notice that it's a very big chunk compared to the rest of the periodic table. Okay, so it's most of our elements. Okay, then we have our metalloids. Okay, so things like boron and silicon. Okay, so they can exhibit properties of metals and nonmetals. They're known as semiconductors because they're poor conductors of heat. And they're also, they can also conduct electricity, but they're rather poor conductors of heat. They're solids at room temperature, generally speaking. Okay, and again, remember they lie along this stair step. But they kind of share the properties of metals and of nonmetals. Okay, lastly, our nonmetals. Okay, so things like sulfur, nitrogen, bromine. They can be found in all three states, gas, liquid, and solid. They're poor conductors, and the solids tend to be very brittle. And again, they tend to gain electrons to become anions. Except for hydrogen, they're located in the upper right corner of the periodic table. Okay, so here's a problem for you to try. Here they just want you to write the name of each element and classify it as a metal, nonmetal, or a metalloid. So grab a periodic table. I have one for you on the Blackboard website if you go to, I think, the course materials, just in case you don't have one handy, or you can Google it, or if you have a chemistry book, it will probably be on one of the front covers or back covers. But go ahead and give these a try. So familiarize yourself with some of the names and symbols. The faster you can get at recognizing, the easier it'll be to understand chemistry in general. And just classify it as a metal, nonmetal, or a metalloid. So use your periodic table and say, is this a metal, nonmetal, or metalloid? Okay, so I'll give you a second to pause, and then we'll go over this one. Okay, so the first one, Na. So what is its name? Okay, so maybe you had to go to your periodic table, or maybe just from talking about it enough at this point, you know that this is sodium. Okay, and whether it's a metal, nonmetal, or metalloid, well, it's on our left-hand part of our periodic table. Okay, so we know it's going to be a metal. Next one, Mg. Okay, so this one, that's going to be magnesium. And is it metal, nonmetal, or metalloid? It's, again, on our left-hand part of our periodic table, so that's going to be our metal. Br. Okay, so it's bromine. And this is a halogen, which makes it a nonmetal. Next one, N, and it's just for nitrogen. And again, this is on the right-hand side of our periodic table. This will also be a nonmetal. It's a gas. So you can kind of tell the things you think of as being gases a lot of times will be nonmetals. Last one, As. As is arsenic. Okay, and that should be right along that stair-step line. Okay, so that's going to be a metalloid. Okay, so hopefully you could determine which of those were metals, nonmetals, and metalloids, and hopefully now you're a little more familiar with some of the symbols if you weren't before. Okay. So let's take a deeper look at this. Okay, so if one thing we have here is we have the main group elements and we have the transition elements. Okay, so notice in our periodic table we have these numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on. We also have 1A, 2A, 3A, 4A. Okay, so these are two different ways of numbering the periodic table, just used for different applications. One was a little older than the other, and they've kind of gone away from using the 1A system, 2A system. Okay, but it's still, you'll still hear people say it, and I think it's still worth talking about. Okay, but what we've done here is we've broken the periodic table into main group and transition. Okay, so the transition metal elements is this block in the middle. Okay, so the transition elements or transition metals. You can say it either way. Everything else is a main group, aside from the inner transition metals, which are the lanthanides. So those are the guys that are down here. Okay, so these are the inner. Just so that we're clear. Okay, so those are the inner transition metals. Okay, we're not going to talk about those right at this moment. Okay, so break this into main group and transition elements. And notice again it's 1, 2, 3, 4, 5. So this would be like group 1 or column 1. This would be period 1 or row 1. Okay, and you may also hear people refer to this as 1A, 2A, 3A, just depending on what information they're trying to convey in maybe when they went to school. Okay, so that's our basic groups here. So if I was to ask you which one of these is a transition element, you would pick something out of this area. Okay, so elements within a column, we often call these families. And that's because they share similar chemical and physical properties. Okay, they have the same number of electrons in their outermost shell, in other words, in their valence. So something like, I don't know, sodium, lithium, these all have a valence of S1. Okay, so they all have the same outermost shell. And the ones that generally have names are going to be our alkali metals. So this is column 1 or group 1A. Our alkaline earth metals, which is column 2 or group 2A. halogens, which is column 17, or in other words, group 7A, and then the noble inert gases, which is column 18, or group number 8A, excuse me. Okay, so let's take a look at these. So here we've kind of color-coded them. Okay, so you can see your alkali metals, your alkaline earth metals, your halogens, your noble gases. These are all going to be your transition metals, okay, in the blue. And then your inner transition metals, your lanthanides and your actinides. So they're named that because of what starts. So lanthanides are named from lanthanum, and your actinides. Lanthanide, excuse me, not lanthanum. Okay, so moving on. Okay, so this is all where all your basic groups are. Okay, notice not everything has kind of a fancy name here, but we do have alkali metals, alkaline earth metals, metalloids, halogens. Okay, noble gases are over here. Okay, so not everything has a super fancy name, but you kind of get the idea. Okay, so let's break down each one of these, or let's just talk about where each of these lies. Okay, so take a look at this. So it says write the symbol, so this time they want you to go from name to symbol. And they want you to classify it as an alkali metal, alkaline earth metal, halogen, or noble gas. Okay, so take some time, pause the video, and try to give this one a try. Okay, so let's look at this one. So the first one, sodium. What's our chemical symbol for sodium? Well, it's an A, of course. And what type of this? What type is this? Either alkali metal, alkaline earth metal, halogen, or noble gas. So if you find it on your periodic table, sodium is going to be in group 1 or group 1A. Okay, so that's of course an alkali metal. Next one, iodine. Okay, so find it on your periodic table. What's the symbol? I. Okay, then what is it going to be? This one's going to be a halogen. Next one, calcium. What's its chemical symbol? This is just going to be Ca. And if you find it on your periodic table, it's in column 2 or group 2, group 2A. Okay, so this is going to be an alkaline earth metal. Next one, barium. It's the symbol, Ba. Okay, similar to calcium. Where is it going to fall? It's 2 elements underneath calcium in the same group. So it's also going to be an alkaline earth metal. And last one, krypton. Okay, what's its symbol going to be? Kr. And it's all the way to the right of our periodic table, which is where our noble gases are. So just be sure that you can identify an element either through its chemical name or through its symbol, and make sure you understand where it fits into the periodic table. So is it metal, non-metal, transition element, that kind of thing, or metalloid? And then make sure you can identify it as, if it has a named group, something like an alkaline metal or a halogen, make sure you can identify all those. Or is it a transition metal? You know, that kind of thing. Is it a main group element or a transition element? So just make sure you can go from symbol to name and from name to symbol, you know, with a periodic table. And make sure you can identify what type of element that is. Okay, so moving into ions. Okay, so we've said that metals tend to form cations. In other words, they tend to lose an electron from their valence. Okay, and we're going to use this phrase, obtain the nearest noble gas electron configuration. And we'll take a look at what that means. But essentially it means that they want to lose or gain electrons, in this case lose electrons, to be more like a noble gas. So more like a noble gas. Okay, so nonmetals, so metals tend to form cations. Nonmetals tend to form anions. So they tend to gain electrons in their outermost energy level, again, to obtain the nearest noble gas electron configuration. Okay, so they want to gain electrons to be more like a noble gas. And I'll show you what I mean in just a moment with the periodic table. Okay, metalloids tend to form cations but can also form anions, so they're kind of a toss-up there. Okay, so that's just kind of our basic idea there. So nonmetals tend to form anions, metals tend to form cations. Okay, so this is what the periodic table might look like if you're talking about charge. Okay, so our column 1 here, 1A, notice that, okay, here we have metals, and notice they all have a +1 charge in column 1. Okay, then we move to column 2, and we have a 2+ charge. Okay, jumping over the transition metals, we have aluminum here, which is 3 plus. Okay, and then everything else, now we have 3 minus, 2 minus, 1 minus. Okay, so what's happening here? So we're going from metals to nonmetals, and we're going from cations to anions. But notice that if we move this way for the nonmetals, or for the metals, excuse me, the charge is increasing in the positive direction. And if we move this way, it's decreasing in the negative direction. Okay, so why is that? Okay, so the reason that is because we want to become more like the noble gases. Okay, so a noble gas and its valence has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence. Okay, and if you're something like lithium, you essentially have this valence, S1. And I know you don't necessarily know what that means yet. That's okay. But what you do need to know is it has 1 electron in its valence. So if it just loses 1 electron, so it would basically be stepping back like this to become a noble gas. Okay, so it becomes more like a noble gas configuration. So it gives up 1 electron, and that gives it closer to a noble gas configuration of 8 electrons. And as I move one more step in this direction, now I have to lose 1 electron, 2 electron, then I become more like a noble gas. So that's why I become 2 plus here, but only 1 plus here. And that's the same for everything. Okay, then if I jump over here to aluminum, so I would have to lose 1 electron, 2 electrons, 3 electrons, then I become more like a noble gas. Okay, so you notice that it's 3 plus. Now what about my anions, so my nonmetals? Notice that they're negative. Well, these are going to gain electrons to become more like a noble gas. So if fluorine just gains 1 electron, then it becomes more like a noble gas. If bromine gains 1 electron, it becomes more like a noble gas. Okay? And then if we move to the left, now we're 2 over. So oxygen needs to gain 1, 2 electrons, and then it becomes more like a noble gas. Same thing with sulfur. 1, 2, then it becomes a noble gas. And then nitrogen, 1, 2, 3. So you can kind of see that. Okay, so these are all known charges. So make sure that you know all of these. So make sure you know your alkali metals, your alkaline metal, earth metals, aluminum, and your halogens, and all that good stuff. Okay? So there's a little trick for remembering this. You can say 1, 2, 3, just skipping over the transition metals. And you're going to skip this one. And then you're going to say 3, 2, 1. What that means is, as long as you remember that your metals are going to become cations, so this becomes 1 plus 1, plus 2, plus 3, and this becomes minus 3, minus 2, minus 1. So 1, 2, 3, skip 3, 2, 1. Okay, and that'll kind of remind you what charges these have. Okay, so taking a look at this with actual dots of electrons. Okay, so we said everything wants to become more like a noble gas. So what's so special about a noble gas? Well, it's this octet rule. Okay, so atoms are very stable if they have 8 electrons in their valence. Okay, and that's sort of what they're striving to do. And when we get into probably next semester, when we get into drawing Lewis structures, you'll kind of see that even come into effect even more. Okay, but if you take a look, so excluding helium, it's happy with just 2. But if you look at neon, 2, 4, 6, 8. Okay, so 8 electrons. Okay, so what's the best way for lithium to become more like helium, or for sodium to become more like neon? It's just to give up that 1 electron in its valence. Okay, so give this one up, and that will become more like neon, because it also has a full shell underneath there. Okay, so just keep that in mind. And then again, if we look at our halogens, okay, so notice they're missing 1 to become more like a noble gas. So if they just gain that electron, then they'll have a full octet. So that's what everything's striving for. Okay, so that's sort of the driving force behind adding or losing electrons to form ions. Hopefully that makes sense. If not, just remember those charges and you'll be fine. Okay, so it says predict the charge of the monoatomic single atom ion formed by the element. Okay, so give it a pause, give it a try, and then we'll go over it together. Okay, so let's just walk through each one of these. First one, A, it's oxygen. Okay, so what's it going to do? So if you remember 1, 2, 3, 3, 2, 1, or if you just remember, okay, it wants to be more like neon. So remember that's going to gain 2 electrons. So of course 2 minus. And that's when we're talking about oxidation state or charge. Oxygen, you should know this one right away, is -2. Just know that one right away. Okay, B, potassium. Okay, so if you find on the periodic table, you see it's in column 1. Okay, so it's most likely to give up an electron to become +1. Next one, aluminum. So this is one that again has a set charge. So aluminum, you say 1, 2, 3. It's in that third 3A. Okay, so we said this one was going to be +3. Again, one you can just kind of memorize and always know that one. Next one, rubidium. Okay, so find it on the periodic table. It's in your alkali metals. So remember, your alkali metals are going to give up 1 electron to become +1. Sodium, again, it's an alkali metal. Those always give up 1 electron to become +1. Chlorine, halogen. Okay, so these are going to want to gain an electron to become -1. Barium. Okay, this will be in group 2 or your column 2. So remember, they want to gain or give up 2 electrons to become +2. And calcium, right there in the same column will of course give up 2 electrons to become +2. Okay, so make sure you can go through and identify charges of the elements. Okay, so if we were to form an ion, what's the most likely ion? Okay, notice that we're only talking about a certain group of these because some of these you have to predict it a little bit differently, and we'll get into that later. But for now, make sure you know that these, those given ones that we can predict easily, make sure you know those. Okay, so I believe this topic will pretty much take us to the end here. I think we get into dimensional analysis right at the end here a little bit, but what is a mole? Okay, so we say that chemistry is quantitative in nature, and its unit is the mole. Okay, so a mole is just a unit that's similar to like a dozen. So if I was to say, get me a dozen donuts, you would know I meant get 12. Okay, well, a mole is like the chemist's dozen. Okay, and a mole is a unit associated with 6.02 times 10 to the 23rd units. Notice I just said units. So I can have a mole of anything. I can have a mole of pennies. I could have a mole of carbon atoms. I could have a mole of elephants. It doesn't matter. Okay, it's just a number that tells me, if I say I have 1 mole of something, that means I have 6.02 times 10 to the 23 of those. Okay, so make sure you learn this number. You're going to use it a lot, so just make sure you get it down. Okay, much easier to memorize it than have to look it up every time, but it'll come naturally as well. Okay, so there's Avogadro's number of units in every mole. Okay, so Avogadro's number is 6.02 times 10 to the 23rd. That's known as the mole. It's also known as Avogadro's number. So 1 mole is Avogadro's number of that thing. Okay. So for instance, 1 mole of copper atoms has an atomic mass of 63.55 grams, which is 6.022 times 10 to the 23rd copper atoms, which is approximately 22 pennies. Okay, so why do I bother telling you that? Well, if you look at the periodic table and you look at copper, okay, so you see it has an atomic mass about 63.55. Okay, notice that's for 1 mole of copper atoms. Okay, so your periodic table tells you information about 1 mole of something. Okay, that's useful information. If we're trying to go from mass to moles, that's good information to have. Okay, and so what this allows me to do, is allows me to do something like this. So what if I wanted to weigh out 1 mole of carbon? Well, I would look at my periodic table and see carbon has atomic mass of 12, which means 1 mole of carbon atom weighs 12 grams. Or say I didn't know that, and I wanted to know, well, how many moles of carbon do I have? Say I weighed out 5 grams instead of 12. Maybe I'm trying to do a reaction. I want to know how many moles that is. Well, I could do the same calculation. Okay, so it's a powerful tool that allows us to go from mass to moles. And the reason we need to go from from mass to moles is because we can't compare masses directly. In other words, comparing a gram of carbon to a gram of, mercury, you're going to have a completely different number of moles. But if I convert them to moles first, then I can compare them. And we're going to be doing this throughout chemistry. Okay, so this is one calculation we're really going to have to get down. Okay, so here we have essentially the mole lets us count atoms by weighing. So 12 grams of carbon-6 is equal to 1 mole of carbon-6, and it's equal to 6.02 times 10 to the 23rd carbon atoms. Okay, so it allows us to weigh things out, know how many moles that is. So if you're in the lab and you're doing calculation, you say, okay, I want to use 12 grams of carbon. How much oxygen do I need to react with this? Something like that. Okay. So it allows us just to use mass as a way of counting. Okay, so 22 copper pennies can contain approximately 1 mole of copper atoms. Okay, so 22 copper pennies is about 6.022 times 10 to the 23rd copper atoms. And yes, I am going to keep saying it until it gets into your minds. Okay, so 1 tablespoon of water contains approximately 1 mole of water molecules. Again, remember, 6.02 times 10 to the 23rd. You're going to get so tired of hearing me say that. Okay, so how large is the mole? We don't have to do this one, but suppose this is just sort of a thought experiment. Suppose you've inherited 1/4 of a mole of pennies. It says if you spent 1 times 10 to the 12th dollars every second, how many decades would it take you to spend your inheritance? Okay, so let's look at this. Okay, so 1/4 of a mole is equal to 1/4 times 6.02 times 10 to the 23rd cents per mole. So equal to $1 per 100 cents. Okay, so we have a 1/4 mole of pennies, which are each 1 cent. Okay, so it's 100 per dollar. That means we have 1.51 times 10 to the 21 dollars. Okay, so 1.51 times 10 to the 21. Okay, so let's look at that. 1.51. I don't even know if I can fit it. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so we end up with this number. Okay, and I'm just writing this out for dramatic effect. Obviously, we know it's a big number. But look at this. So, thousands, millions, billions. Okay, that's a lot of commas. Okay. So what's my point? The point is there's a lot of money. Okay, and they're asking us if we spent 10 to the $12 every second, how many decades would it take us? So they've done the math there for us. We don't have to go through it. It would take you 4.79, almost 5 decades, almost 50 years, if you spent 1 times 10 to the $12 every second. Okay, so what's the point? It's a lot of money. The mole is very, very big. And that was just for 1/4 of a mole of pennies. Okay, so imagine if we had a full mole of pennies or a full mole of dollars. Okay, so this number is huge. That's what I'm trying to say. So how large is the mole? It's very, very big. It's almost inconceivably large. Okay, so how are we going to actually use this? Okay, so now you understand the mole is big. What's the point? Okay, so the point is we can go from mass to mole. So if we want to compare how much of an element we have, we can't really directly compare the mass. So that helps us in one way. But if we were to interested in something like, well, how much of this do I need to react with how much of this? Okay, we have to compare in moles of the element. And we can't say that I'm going to react. Well, we could say that I want to react this much mass with this much mass. But if we wanted to make sure our reaction is complete, or if we want to determine how much we actually need and make sure we have enough, that kind of thing, we have to go into moles. And the way we do this is just by going through the atomic mass. So if we're given the mass, and again, this is your dimensional analysis, so following your units. So given the mass, we're going to take our atomic number. So remember on the periodic table, those numbers tell you grams per mole. Okay, so if we want to undo mass, we're going to put the mass part on the bottom. So this is our grams part, this is our moles part. Okay, so if we were to do this multiplication and everything, this math, grams would cancel with grams, and we're left with moles. Okay, so that's your dimensional analysis part. So you can just follow the units to get to where you want. Okay, so as an example, suppose I wanted to know how many moles of carbon atoms is in 24 grams of carbon. Okay, so I go to my periodic table, I find my molar mass for carbon, which is 12. Okay, and I'm essentially just going to divide by my molar mass. Why? Because that cancels my grams, left with moles of carbon, and that's what I wanted. So 24 grams of carbon is 2 moles of carbon atoms. Okay, pretty easy. And this doesn't matter whether I have 1,000 grams, 1 gram, 10 grams, it doesn't matter. Okay, so just divide by the molar mass, that gives you moles. If you can't remember that, just remember to do your dimensional analysis, and that will get you to where you're going. Okay, so I'm going to go over some of these, and I'll do an example for you. Okay, so what if I want to go from mole to mass? What's very similar, okay, so after we do our mole calculation, and we compare, okay, I need 2 moles of this for every 1 mole of this, well, now I want to go weigh it out, because that's where it's useful, right? Okay, so now I want to go back to mass. So suppose I know the number of moles, and I know the atomic mass from the periodic table, and this would also work for molecules. That will get me to mass. So I multiply this time. So remember, moles here cancel with moles. I'm left with the atomic mass, which is in grams. Okay, so that's going to get me where I'm going. So here I have 8 moles of helium. I want to know how many grams that is. So I'm just going to go straight to my periodic table, find the molar mass of helium, which is 4, and I'm going to multiply that. And just to do dimensional analysis, your moles of helium will cancel with moles of helium. You're left with grams of helium. Okay, so that's all you need to do. Just multiply by the molar mass, and that will give you the number of grams. Okay, and we can do these in multiple steps. So I can go from mass of the element to the moles of the element to the number of atoms of the element. Okay, so suppose I had the mass of something, and I wanted to know how many the number of atoms that was. So this is where my Avogadro's number comes into play. Sorry, this should be raised to the 23rd. Not like that. So forget about that. Raised to the 23rd. Remember, 6.02 times 10 to the 23rd. Okay, so I have the mass. Suppose I want to go to moles, divide by the atomic mass, and now I want to go to atoms. So here grams cancel with grams, moles cancel with moles, and I'm left with atoms. So I put my Avogadro's number on top so that I leave with atoms. Okay, so as an example, suppose I want to know how many the number of atoms in 45.99 grams of sodium. So divide by my molar mass, that gets rid of the grams. Now I'm in moles, and remember that for every 1 mole, again this should be raised to the 23rd, for every 1 mole we have 6.02 times 10 to the 23rd atoms. Okay, so remember 1 mole of something is Avogadro's number of that thing. Okay, so if I cancel moles here with moles, I'm left with atoms, and that's what I'm looking for. So I would do 45.99 times Avogadro's number divided by 22.99, and that will give you my answer. Okay, so make sure you can get comfortable doing those. And I could go the other way around. The only thing that changes is the placement of our conversion factors, or whether they're right side up or upside down, so to speak. So if I want to go from atoms to mass, I have to first divide by Avogadro's number to get back into moles. Remember, there's this many atoms and 1 mole of an element. Okay, then multiply by your atomic mass. Okay, so this gets rid of number of atoms, this gets rid of number of atoms, this gets rid of mole, and left with atomic mass in grams. Okay, so it's just using those conversion factors in a way that gets you to where you want to go. So that's using the dimensional analysis part. Okay, so for this one, they want us to determine the number of sulfur atoms in 86.6 grams of sulfur. Okay, so give the video a pause. Give this one a try. Let's see what we come up with. Okay, so the first thing I want to do here is just start out from what I know. So I know that they're giving me 86.6 grams of sulfur. So another piece of information that will be helpful here is to know the molar mass of sulfur. So the molar mass of sulfur is equal to 32.07 grams in 1 mole. What we want to know is how many atoms of sulfur this is. Okay, so just write out what you know, write out what you don't know. Remember that 1 mole is equal to 6.02 times 10 to the 23rd atoms. Okay, so let's just set up our dimensional analysis. So we're starting from 86.6 grams of sulfur. I'm going to draw out my dimensional analysis. Okay, so the first thing I want to do is what? I want to get to atoms. So what's the first thing I should do? I should go to moles first, right? So for every 1 mole of sulfur, I have 32.07 grams of sulfur. Okay, so that puts me into moles. But what I ultimately want is atoms. Okay, so how many atoms? Okay, so now I know that for every 1 mole of sulfur, I have 6.02 times 10 to the 23rd atoms. Okay, so now if I'm going to plug this into my calculator, I'm going to do 86.6 times 6.02 times 10 to the 23rd divided by 32.07. Or remember, you could do this out this way, 6.6 times 1 over and then times 6.02. Okay, those will all give you the same answer. And the answer I came up with here is 1.63 times 10 to the 24th. Of sulfur. Okay, so that would be my final answer. Okay, so that will end chapter 2, and that will end the lecture for today. Hopefully this is all making sense. If not, go see our friends at the SLC. Look up on YouTube. There's lots of people explaining this in different ways. But go see our friends at the SLC. Email me. Set up office hours with me if you need. And hopefully you can find all the help you need to get you where you're going. Okay, I will see you next time.